Welcome students to our next class of manufacturing processes. We were reading the metal forming processes, and we already continued our classes till this plastic deformation and yield criteria. So previously I have discussed with you the stress strain curve, work hardening, and we already started the principle of metal forming theory. I already covered the true stresses, true strain as well. Now, today we'll be going to the yielding criteria. This is very important, and you must have an idea as because it is in your syllabus as well. So this is the very important criteria for yielding. So you can take a screenshot of this one if you wish, or you can just write it somewhere else, as because this is very important for your semester examinations as well. So now let us try to understand what this actually means, this yielding criteria. In yielding criteria, you already have heard the yielding in stress strain curve while discussing with the ductile materials. We already discussed about the phenomenon of yielding. Yielding means when you are applying a small amount of force, you are getting a huge amount of deformation. That means here the stress and strain are not proportional to each other. So by applying a small amount of the stress or load, you can say the material deforms plastically. That is the phenomenon known as yielding. Okay. So as because after the yielding, the plastic region starts, as I earlier told you in the stress strain diagram. So yielding criteria is very important for metal forming process, as because whole of the metal forming process, the first assumptions in yielding criteria is metals are homogeneous, okay, continuous and isotropic. Okay. Next, same yielding strength. So you can guess from this first one, homogeneous, same composition, that means same composition. Okay. Same yielding strength in tensile and compression loading, that is ductile materials. Okay. So same yielding strength in tensile and compression. So that is happens only for ductile metals. But in case of brittle, it is not valid actually. So we are not dealing with the brittle materials in case of yielding criteria, or you can say the working of metals. Okay. Now the volume is constant during plastic deformation. This is very important. So in the numericals, will be going this concept. We'll be using this concept to solve numericals. Before metal forming and after metal forming, the volume will be constant. So we'll be taking this concept in consideration while solving the numericals on different metal forming process. That is very important. You must take a note. And the sum of the plastic strain increment is 0. Plastic strains increments. Epsilon 1, epsilon 2, epsilon 3 should be 0. Strain rate and temperature effects are not considered. Okay, so no problem. Now, this one. These are the things I was talking about. Two yielding criteria are commonly used to predict when yielding starts for complex state of stress, namely von Mises and Tresca criteria. So we will be dealing with these two criterions only, as because there are mainly 4 to 5 failure theories we generally used to read in our machine design, and here we are dealing with the ductile materials actually. So we'll be sticking to the design of the ductile materials. So we'll be mainly considering von Mises and Tresca criteria, as because although there are many criterions, I think around 2 more criterions are there for describing or for designing the ductile materials. One is there for brittle materials only, that is the Rankine is only the criteria, maximum principal stress theory for Rankine materials, brittle materials only, but left 4 generally we used to predict for designing of ductile materials. So let us have an idea on von Mises and Tresca criteria. Okay. So in tresca criterion, it is also known as, this is actually Guest and Tresca. Okay, they are the scientists, they have developed this or proposed this type of criterion for designing of um, ductile materials. Okay, actually failure design of ductile materials. So tresca criterion, or you can say Guest and Tresca, also known as the maximum shear stress criterion, maximum shear stress. Okay, so in tresca criterion, what happens, the effective stress is given as this one: sigma max minus sigma min should be greater than equal to sigma y, or sigma 1 minus sigma 3. Look, this sigma 1 and sigma 3 are maximum, you know, the stresses. Actually they are, these are the, this, you know, the shear stress criterion. Okay, so sigma 1 and sigma 3 should always, this one is a shear stress. Okay, so difference of the, you know, sigma 1 and sigma 3 should always be greater than equal to sigma y, and where sigma 1 greater than sigma 2 greater than sigma 3. So you can see maximum is, say, the sigma 1, and minimum is the sigma 3. You can easily guess from this condition. So sigma 1, sigma 2, sigma 3 is given as here. So difference of the maximum and minimum nominal stress, you can say, should always be greater than equal to this shear stress. So that is the tresca criterion. Okay, now the effective strain is expressed as follows: d epsilon should be mod of, you know, d epsilon 1 max, where I is the 1, 2, 3 for the three principal direction x, y, z. That is the criterion. So this thing is the main thing for tresca criterion. Actually, this is the yielding criteria we are going to have while designing, you know, while working on the metals, ductile metals actually. So tresca is one of the most important one. Okay, now coming to the von Mises yield criteria for ductile solids. So it says material yields under von Mises yield criterion if and only if the von Mises equivalent stress in the 3D object is greater than or equal to yield stress, that is the sigma y. Okay, there is a measured quantity, you can say. Okay, so this, thus yielding occurs if 1 by root 2 of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square whole square actually plus sigma 3 minus sigma 1, that whole square should be greater than equal to sigma y, where sigma y is the yield stress. Okay, in terms of principal stresses in the 3D solid. However, if stresses in the xyz are provided, the above expression is modified to, actually stress is a tensor quantity, so they can write it as sigma xx, sigma yy. Actually these are the normal stress when you are considering the tau, that is the xy, then you have to write tau xy or tau xz, tau yz similarly. Okay, so this is a normal stress, so xx, so this is one the normal stress. So sigma xx minus sigma y, this one also represents the same thing. Okay, this one same thing. So sigma xx minus sigma yy whole square plus sigma yy minus sigma zz whole square plus sigma zz minus sigma xx whole square plus 6, this one, look, I was talking about tau xy square plus tau yz square plus tau zx square. Okay, so mutually perpendicular axis only shear stress is present. That's why they are giving the tau xy, not xx, that is the normal stress, and this one is the shear stress. So this whole thing under root divided by under root 2 should always be greater than equal to sigma y, that is the yield stress. So that is the two criterion, very important. So you can take a screenshot or you can note it somewhere else. So one is your you know, this one is the tresca criterion and this one is the tresca criterion, that is the maximum shear stress criterion. So you can take a note or take a screenshot. That is a very important thing you must need to know for under the heading of the yielding criteria. And the next one is von Mises yield criterion for ductile solids. So these two main, this failure theories is very important for your yielding criteria as well. Okay. Now, there is one last thing I would like to share with you. That is this. You can see over here. Just I will show you here. Look, if your this nominal stresses comes under the envelope, this whole envelope, the outside envelope, this envelope is the von Mises, and the inside, you can see over here, the inside, this one, this polygon, you can see. Okay. So this polygon is for tresca, that is maximum shear. Okay. And this outside, this elliptical region is for von Mises. So what does it means? If you are considering von Mises, then these points outside the polygon is also safe for your ductile materials. These points, okay, inside is always safe, but these points are always safe for von Mises if you are considering von Mises. But if you are considering tresca, then this region is safe up to the polygon. Okay, if you are considering tresca. If your normal stresses lies inside this region of this polygon, then you have a safe design for your ductile material, or working on the material is safe. But if the stress is developed outside this particular polygon, say this one, say this one, say this one, or this one, or this one, or this one, then it is not safe, as because your material will develop crack and eventually it will break. Okay. Now, if you are considering this von Mises, say this von Mises, then if the points comes outside the envelope, then it is not suitable for according to von Mises as well as tresca also. So why designing, or you can say here we are dealing with the this metal working processes. So you have to keep in mind that your this, you can see over here, these are the points. It says the yielding at this axis, sigma 2. This is the sigma 2 axis and this is the sigma 1 axis. Okay. So for these two principal stresses, these two are the principal stresses, sigma 1 and sigma 2. For these two principal stresses, you are having sigma yield over here and this one. These are the 2 points. For here it is here and it is here. So if your stresses are the stresses developed during working of the metals, whether it is hot working or cold working or forging, whatever it may be, just think of metal forming process. If your stresses are within this graph, say your stress is this one or this one, then your material is safe to be hot work or cold work or forged work or whatever metal forming process. But if somehow the stresses developed during hammering or extrusion or whatever, maybe the cup drawing or bending, hot working or cold working, whatever, if your stress developed is somewhat crosses this point, sigma yield, and comes here, then it has a chance to deform. Okay. And it will eventually develop crack and afterwards it will break. Okay. So after this point it will yielding will take place. And remember one thing, that if yielding takes place in ductile material, then it is unsafe to use, as because we will not be waiting until the material breaks down. So we will just scrap the material then and then only when it will just start yielding. So yielding is the limit of our use of particular material. So you cannot wait for the ductile material to break. Not in that case of brittle material. In brittle material, it will directly break without giving you any warning. as because there is not such clear yielding point. Okay, so in ductile material there will be a warning from the material that I am not unable to bear the load you are giving to me. So that is the yielding point. So if your metal is yielding, that means you have to scrap the metal. So you have to keep in mind, inside this region, this whole region, your material is safe to be hot worked or cold worked or any metal forming work. After this point, if you are working or say your stresses is developing somewhat beyond this region, then your material is not good to be metal forming process. That I want to tell you, and I was very much eager to tell you, as because as an engineer you must need something, there should be some guidelines. You just cannot take a hammer and just repeatedly hammer a certain material to give it a desired shape. You must obey some rules, regulations. So these are the rules and regulations you have to keep in mind while metal forming process and performing the metal forming process, different metal forming processes. Okay, so this is your guideline, that you have to keep the stresses produced in the particular metal forming process. You have to keep the stresses produced in that particular material within this safe region, that you have to keep in mind. Okay. So what we learned today, that in principle of metal forming theory, the yielding criteria plays a very important role for the safe keeping of the material you are going to hot work or cold work or any metal forming process you are going to apply on that particular material. So there are two mainly yielding criteria we have to keep in mind while working on the materials. That is the tresca criterion, or also known as the maximum shear stress criteria, and the second one is your von Mises criterion. Okay, so I'm just not going to the mathematical derivation of this particular formulas or solving numerical problems, going into very depth of these two theories. If you want, I can make a separate class for these two yielding criteria as well. But for now, I think for a metal forming process, you just need to know the yielding criteria. That's, I think, is enough for you, as because they will be asking you questions rather on different numericals on particular extrusion process, or this they are very eager to ask questions on rolling process, especially on rolling, then drawing process, cup drawing, so that portion you have to keep in mind while studying this metal forming process. You don't have to so much worry about this numerical portions of this von Mises criteria. You have to worry this in your metal machine designing classes. Okay, so for manufacturing process, you just need to worry about the numericals that are being arising out of rolling process or forging process, drawing process, etc. Okay, so we will try to move on to the metal forming process. Okay, and we will try to have some extensive knowledge on the this metal forming process in details. Okay, so just to give you a small overview for the next class, I'd like to share you again that I previously shared with you, that metal forming processes are mainly classified into two main criteria, that is the sheet metal working we are dealing with, and bulk deformation. Okay, so in detail we will be studying in the next classes. For today only, I will be stick onto the basic things, basic classification of metal forming process. In sheet metal working, it says the surface area or volume is very large, and the process mainly we are concerned about the sheet metal working are the bending operations and shearing processes, deep or cup drawing as well. And we'll be having a separate classes on this particular operations. We'll be learning a lot around. These are the most important and most exciting as well, interesting topic you can say also. So we'll be learning so much extensively in our later classes. And for this bulk deformation process, we will be having where surface area or volume is very small. Okay, that includes the rolling process, the forging process, the extrusion process, the wire and bar drawing process. So you have to keep in mind that metal forming processes are being mainly classified as sheet metal working and bulk deformation. In bulk sheet metal working, we are having surface area or volume is very large, as you can guess from the sheet metal, as because the sheet metals are somewhat having a large surface area. Okay, so in sheet metal working, we will be having bending operations, similarly shearing process or deploying, and in bulk deformation, the surface area or volume will be a bit smaller than the sheet metal working. So in the coming classes, we'll be discussing in details the different processes of metal forming processes. So stick with MechPro classes, and we'll be learning a lot about the metal forming process as well. So thank you for watching today.